Okay, we are ready. So, okay, hello everyone in the auditorium here and online. It is my pleasure to introduce our speaker today, Masha Baryakhtar. Masha is a leading theoretical physicist developing novel search directions for axion-like particles and other physics beyond the standard model. These include precision laboratory searches for weakly coupled dark matter, astrophysical and gravitational wave observations that can shed light on the presence of possible new ultralight particles. Masha received her PhD from Stanford and was a postdoc at Perimeter Institute and New York University, and she is on her way to join the faculty of the University of Washington. Today, Masha will tell us about searching for new particles in the sky. So for the audience here, please interrupt Masha with questions if you have any questions as we go along so that the talk is as informal as possible. And for those on Zoom, please put questions into the chat, which I will monitor and try to ask right away from Masha. So in case there are online questions, I will be interrupting Masha today. So please go ahead, and we are very happy to have Masha today.
Thank you. Let me know if there's any issues on the Zoom end or on this end. Things well done. Thanks everyone for being here. It's a real delight to be here in Aspen and giving a talk in person. It's always great to be in Aspen, but I think especially this year, it's very special for a lot of us. It might be the first conference we've been to in a long time. I know the last time I gave an in-person talk was actually right up here in Aspen winter 2020. So it's very nice to be talking to a room full of people. And as was said, please do interrupt with questions. I like to make sure that everyone's on the same page. So today I'll be talking about searching for new particles in the sky. Unfortunately, I haven't seen any of the Perseids yet, maybe tonight. But today I'll be telling you about how to look for axions. And to start off, let's situate ourselves to where we are today. We live in a time of the standard models. There's the standard model of particle physics and the standard cosmological model, which describe the set of particles and interactions that govern our universe. And they've been extremely successful, both on the cosmological side, where there's precision observations with the CMB. There are many data sets which point to the same kinds of parameters that describe the evolution of the universe. We've discovered gravitational waves in the last 5-ish years. So it's a beautiful picture that really tells the whole story of our universe. On the particle side, we've also been very successful. In the last 10 years, we've discovered the Higgs boson, which is the final piece of the standard model. And precision experiments have really gone to more and more decimal places, more and more loop factors in agreement between experiment and theory. So everything is really beautiful, but of course, as we all know, this is not the complete story. In the lambda CDM description of cosmology, we don't really know either what is lambda or what is CDM, and we would like to find out. On the particle side, we have lots of open theoretical questions. Why is the Higgs so much lighter than the quantum corrections that we calculate for its mass? Why is the electric dipole of the neutron so small? How will gravity be modified up at the highest scales? Will we ever have any experimental handles on that question? So today, I'd like to focus on 3 of these kinds of questions and how we can hope to address them. There's one which is a theoretical puzzle, the strong CP problem. There's the experimental observation that there's a dark matter, which we think is a new particle or particles. And once we get an answer to these 2 questions, we might even be able to learn something about the very highest scales in our theory. So this brings us to my favorite particle, the QCD axion. And let's see how it can briefly review how it can address some of these questions. So starting with the strong CP problem, excuse me, we theoretically expect significant charge and parity violation in the potential of the strong interactions. And this would, the presence of such CP violation would give the neutron an electric dipole moment. So here's a neutron with a spin and a dipole moment. To see that in the presence of CP, or in this case, let's just look at parity, the parity symmetry, you can see easily would forbid the presence of a dipole moment of a neutron, because under a parity transformation, the dipole, which is a vector, would flip, whereas the spin, which is a pseudovector, would not flip, and the dot product would not be invariant. And as soon as it was realized that CP violation in the strong sector would manifest in the neutron electric dipole moment, it was already realized that this was an issue, because while the expected value is very approximately, the neutron size times its charge down by a loop factor, that's actually a much more complicated calculation, but this is the number you get. The experimental upper bound is 10 to the minus 26. So there's this parameter theta, which parameterizes the amount of CP violation in strong interactions. And this parameter has to be less than 1 part in 10 to the 10. As theorists, we like to say that this is a large tuning, and we want to try to explain it. Luckily for us, there is a very elegant solution to this problem, which was proposed in the late 70s by Petcher and Quinn and expanded on by Weinberg and Wilczek, which is to solve this issue by promoting this theta parameter, which tells you how much CP violation there is in the strong sector, to a dynamical field, which we then call the axion. So since it's a dynamical field, it can take on different values. In particular, the strong interaction gives the axion a potential, drawn as a cartoon here. It gives it a mass which is usually very light, inversely proportional to some high scale f. This is the decay constant of the axion. And given this potential, the axion likes to relax to its minimum, which is CP conserving. And that gets rid of any kind of manifestation of the CP violation in, say, the electric dipole moment of the neutron. Once the axion was proposed as a new particle, people realized over the next decades that axions are actually very useful in many other ways, and they tend to pop out in unexpected places. In particular, axions also come out of very high energy theories. If you have models with, say, extra dimensions that have gauge fields which propagate in these extra dimensions, axions can be the low energy remnants of those compactified gauge fields. And this happens in models, in particular in many models of string theory. And just like QCD gives a potential to the QCD axion, other axions can acquire potential and a mass that's some non-perturbative gravitational contribution, which may be large or small, but you do expect in these models to have multiple axion-like particles. Now you might say, okay, that's very nice that there's this, that some of these theories predict other axions, but what are they really useful for if we're just particle physicists doing our low energy experiments? Another thing that these axions can do is be the dark matter of the universe, which is the big topic of the workshop that I'm part of these weeks. So axion particles or any other ultralight scalar particles act as cold dark matter of the universe, and they can be naturally generated during a period of inflation. So if you have a axion with a potential, It'll have some initial value in our universe that's determined randomly by inflation. And over time, the field value of the axion behaves just as a damped harmonic oscillator with frequency given by its mass and friction given by Hubble, by the expansion rate of the universe. So early on, when Hubble is small, the value of the axion field is frozen by Hubble friction. But then when the universe expands enough, Hubble drops below the mass, and the field begins to oscillate, and the energy dilutes just as non-relativistic matter would. So the axion is an excellent cold dark matter candidate, and many experiments today are looking for it in exactly this capacity. And this can be the case either for the QCD axion or for axion-like particles. So here I'm showing the parameter space that we'll be talking about today. The axion mass is on the x-axis in electron volts, and the axion coupling, or its maximum field value, is given on the y-axis, this Fa. The QCD axion is a line. As I said before, it's generated by QCD. Its potential is generated by QCD. And in principle, the QCD axion can be the dark matter basically anywhere on this line. If you have more general axion-like particles, which have nothing to do with solving the strong CP problem, they can also be a dark matter approximately along this line. If you say you take the most generic initial condition for the value of the axion field, you'll be in this darker band. To get all of the dark matter as you go higher, you need to tune the initial condition close to the top of the potential. So it's harder and harder to get all of the dark matter here. If you go below the blue line, you can create too much dark matter unless you start with an initial condition that's very close to the bottom of the axion potential. That said, there's many people in this audience who have thought of various interesting theoretical tricks to basically populate most of this parameter space where the axion can be the dark matter. But these are kind of interesting parts of the parameter space to be focused on. Unfortunately, as you can see here, or fortunately, depending on your perspective, there's a large open parameter space. And in a lot of it, the axion is extremely weakly coupled. So its coupling both to itself and to other fields in the standard model is proportional to 1 over the scale f. So down here, it's basically gravitationally interacting. So how do we hope to look for such weakly coupled new particles? For that, so just to summarize, this is why we like the axion. So it could solve the strong speed problem, could make up the dark matter. And given that it's comes from such high scale physics, either you can think of it as a string theory, or you can just say the symmetry that gives rise to this pseudo-Goldstone boson is very, very high scales. If you do find such a particle, it's going to tell you something interesting about these very high scales. So we are very interested in trying to look for this particle. Now the question is, how do we go about it? Today, I'll be talking about how you can look for axions from the sky, and to give a bit of motivation of why you'd want to look in the sky, we can just go to the history of physics. How do we look for the weakest particles that we already know? And in fact, something like the neutrino is very efficiently produced in the sun, even though it's extremely weakly coupled, much more weakly coupled than photons and electrons. But the neutrino, the power that the sun emits in neutrinos is not that much smaller than the power that the sun emits in photons. And the reason is, there are two reasons. One is the sun is hot, and the other is the sun is big and dense. So the sun is hot means that neutrinos, which are coupled to us through a higher dimension operator, have a slightly larger coupling because of their high energy than they would have if they were emitted at rest, because of the high temperature of the sun. And the other reason is that the sun is big and dense, so that even though you produce many, many photons, they take a long time to get out of the sun. So effectively, you're just emitting photons from the surface of the sun. whereas you're emitting the neutrinos from the entire solar volume. So you can compensate for the much smaller coupling with the fact that you're competing surface and volume emission. And since I am sitting in Beta Hall, I wanted to also put a historical note in here. So Bethe was used the neutrino to describe nucleosynthesis in the sun just 8 years after neutrinos were proposed as hypothetical particles by Pauli, which I find extremely impressive that they're already being used to explain processes in the sun. And this was kind of well established by the time that neutrinos were first detected directly in the laboratory. So they were not detected until almost 20 years later, after they were already used to understand solar processes. So these astrophysical objects can really teach us a lot about the presence of these very light particles. So just like neutrinos, we can take the axion and produce it in the sun. For similar reasons, you can get non-negligible axion emission even at these very in these parameter space where it's very, very weakly coupled. And we can take this even further. If we say that the sun is good for probing weak particles because it's hot and dense, let's take the next, the even better thing, which is a neutron star. A neutron star is even hotter and even denser. During the supernova, it's so dense that even neutrinos don't free stream out, whereas axions can still free stream out. So here, the axion flux from a supernova can be considerable, even if it's very weakly coupled. So these astrophysical objects can teach us a lot about these very light particles because they can produce them in very large quantities very efficiently. And you can see this on this parameter space, other than some very outstanding experiments that are being done to look for axion dark matter. Basically, the only constraints here, or most of the parameter space that's constrained, is exactly from looking at the supernova and looking at the sun. So it's this gray region up here. So that tells us that we should be looking at other ways to try to produce these axions in large abundances and see if we can learn something from other astrophysical objects. And to go to even weaker couplings, we can go to even more dense and exotic objects. And that's the focus of my talk today, which is looking at black holes. There's a beautiful story of how rotating black holes can populate clouds of weakly coupled bosons, in this case axions, for a process called superradiance. And this will allow tests of these ultralight and very weakly interacting axions in parts of parameter space where it's really very hard to test them in any other way. Questions, comments?
Do you have any idea if we observe the next supernova and we are prepared for it? What will be the sensitivity if it is similar to the 1987?
That's a good question. I don't know if Volodymyr is here, but yeah, I think we'll have definitely better sensitivity because we'll have super K. But by what order of magnitude, I don't know. Yeah.
When you mention making axions and neutron stars, you mean in the supernova event that gives rise to the star?
Yes. Oh, thank you. Yes. So the question is, when are the axions produced in the neutron star? And so what I was referring to with the bound that I drew is the axions being produced in the supernova explosion and free streaming out, and that cools the supernova to if there were enough axion production, it would cool the supernova too quickly for the neutrino burst that we do observe. There are, however, other constraints from just cooling neutron stars done by Sanjay Reddy and others, which observe hot neutron stars, and there's some flux of axions that can be emitted. And if you can put bounds on how quickly they cool, and from that also infer pretty similar constraints. Yeah. Okay, so let's talk about black holes and ultralight axions. Before I get into black holes, I want to tell you about superradiance, which is actually a very general, simple process that has nothing in particular to do with black holes themselves. So let's start with just a kinematic example, which is picture a cylinder that has a friction full surface, so some sort of rough cylinder. And if you throw a ball tangentially to the cylinder, it will slow down because of the friction between the ball and the surface of the cylinder. However, if you spin up the cylinder, so if the cylinder is rotating, once it starts rotating fast enough, the ball can actually speed up as it passes by the cylinder, because the friction will kind of push the ball forward as it's passing by the point of contact. Very importantly, this effect depends on the dissipation, on the friction between the ball and the surface. So in order to extract energy from the cylinder, you need this kind of lossy mechanism interaction between the two. So the same thing can happen for waves. And it was realized by Soldovich and his school that a rotating cylinder that's absorptive to waves, a great example of that is a black hole. So a black hole is a perfect rotating absorbing object, as good as you can get. And a wave scattering off a rotating black hole can be amplified as it passes by under the same conditions as for the cylinder. If the angular velocity of the wave, so its energy over its azimuthal number m, is smaller than the angular velocity of the black hole. And again, importantly, the rate of growth is proportional to the initial amplitude of the wave and also the rate of dissipation at the surface. So the black hole is a perfect absorber, which means that if it rotates at infinity, it looks like it amplifies the waves by a large amount. And this process has been known studied very well in general relativity for many decades. In particular, this is a recent numerical GR simulation of a gravitational wave scattering off a rotating black hole. So you see an incoming gravitational wave that's being rescattered at a larger amplitude because it's extracted the rotational energy of a rotating black hole. And so this is nice, very exciting. You can extract energy from black holes, but depending on the spin of the particle that's coming in, if it's scalar or spin 2, the most you can extract in a one-pass scattering is increasing the amplitude of the wave by a few percent for a scalar, or maybe a factor of 2 for a gravitational wave. So while it looks spectacular in this video, far away, you're not really going to see any big difference. But something exciting happens when we start to trap these waves close to the black hole. So one toy example is surrounding the black hole by a perfectly spherical mirror. And in this case, you can trap the waves next to the black hole. So you can start with, say, a photon that comes in that satisfies the superradiance condition. So the angular velocity is slow compared to the rotation. It'll get amplified and rescatter from the mirror. It'll get amplified again. And eventually, the radiation pressure inside the black hole will become so large that the mirror will explode, because the amplification becomes exponential. The particles are bosons, and the more particles there are in the wave, the faster the growth becomes. So this thought experiment was called the black hole bomb by Press and Tucholsky in the 70s. Of course, it's not a very practical experiment. or weapon, because we don't have perfectly spherical mirrors in nature, let alone around black holes. But we do have something that's basically just as good, which is gravitationally bound states. So if you have a particle that has a mass, it can form stable gravitationally bound states around the black hole. And these states behave just as the trapped states of the photons inside the mirror. For a massive particle, what you want is you want the gravitational potential to be close to the black hole size so that the superradiance energy and angular momentum extraction is the most efficient, which means that you want the particle wavelength to be close to the black hole size. That's why I'm talking about very light particles here whose wavelength can be on the size of astrophysical black holes. And again, the fact that black holes rotating black holes are unstable in the presence of ultralight particles has been studied mathematically as long ago as the 70s, but it was realized by Taki and Dubovsky and others more recently that this is a great probe of beyond the standard model physics in our universe and in our galaxy. And that really started off the field of superradiance as a probe of beyond the standard model physics. So let's talk about it in a bit more detail. What do these bound states look like? Far away from the black hole horizon, the potential is just a 1/r potential. And so we know how to solve this problem. The solutions are just the same as hydrogenic wave functions of the electron going around a proton in a 1/r potential. So I'll be talking a lot about these states labeled by principal number n and angular numbers L and M. And you can have in the back of your mind these kinds of wave functions. I do want to emphasize that all of the axion configurations that I'll be talking about are very classical. These are going to be macroscopic classical field configurations, but they have the same description as these hydrogenic wave functions. And by analogy to the hydrogen atom, you can describe these states by these quantum numbers and the fine structure constant, which is just the gravitational binding between the black hole and the axion, which the mass of the axion I'll be calling mu here to not confuse it with the angular momentum number m. And so this alpha parameter will tell us basically everything we need to know about how these gravitational atoms behave. For example, the radius of these axion clouds scales as 1/alpha times the axion mass, just like the Bohr radius in a hydrogen atom. But now alpha can vary from black hole to black hole. And typically for the parameters we're interested in, it will be a few to a few hundred black hole radii. Of course, two very important differences from hydrogen. One is the occupation number. Unlike electrons, these are bosons, so you can have exponentially large occupation numbers as big as 10 to the 75, 10 to the 80 particles in one state. The other important difference is that unlike hydrogen, we have a proton, where we have a proton in the middle. Here we have a very lossy black hole surface. So that violates unitarity and gives you a little of the wave function and gives you a little imaginary piece to the energy. So the energy of each axion is given by its rest mass, then the binding energy, which we recognize from hydrogen. But now you have an imaginary component, which is exactly the superradiance rate. And it's parametrically smaller than the rest mass, and it can be positive or negative, depending on if the bound state satisfies the superradiance condition. So these axions are non-relativistic. So the superradiance condition is just comparing the mass over the angular momentum number to the rotational velocity of the black hole. And if a state satisfies the superradiance condition, that is the phase velocity of the axions is slow compared to the black hole rotation, these states will grow exponentially. So let's see what this looks like. Question, yes, please.
So these objects you're looking for are odd under time reversal. They're violating CP, so they're violating T as well.
Yeah, the time evolution. Oh, sorry. Yes, thanks. So the question is if they're odd under time reversal. Yeah, so there's a loss between it's a one-way absorption, but it in fact I mean you can run time backwards and the cloud will get reabsorbed into the black hole. Yeah.
I guess that was my question, because a rotating black hole in at least some frame of reference is time reversal odd. So should you not have some signature in your experiment of the time reversal of the axion, time reversal oddness of the axion as it passes over the rotating black hole?
So is there a signature in the axions of the fact that the black hole state kind of violates time invariance? I mean I guess the black hole itself can be oriented in any direction, right? So depending on each individual state of the black hole locally violates time invariance, but the solution can be applied to it rotating in any direction. But it's true that the black hole axis picks out a particular direction, and that will determine which bound states form and what the axions will look like at infinity. So based on so what we'll see is that these clouds of axion form, and then you can observe them, and the state that forms will be directly related to the direction of the black hole spin. I don't know if that answers your question.
But that's not being used in the detection scheme.
That's not directly being used, right?
That's what I would like.
Okay, yeah, thanks. Any other questions? Okay, so let's see how this process happens over time. So if you have a new light axion in your theory, say 6 times 10 to minus 13 eV, just to pick a number. Here I'm showing the black hole parameter space with a spin from 0, which is non-rotating, to 1, which is an extremal black hole, extremal curved black hole, and the black hole mass is on the x-axis in units of solar mass. And to guide the eye, I've shown these blue regions in which the black hole is rotating fast enough to satisfy the superradiance condition for different bound states. For an axion with angular momentum 1, 2, and 3. So if you're in the blue region, you expect the black hole to superradiate and populate these bound states of axions. Just to be clear, there's necessarily no incoming axion wave that's being rescattered. Instead, the black hole grows this cloud of axions around it from any sort of background population of axions, which can even be quantum fluctuations. So you don't require any kinds of axion abundance for this process to happen. And once the black hole is born, say with a high spin up here, it will spin down in about a year for the parameters I've picked until its angular velocity matches that of the axions, which is on this line. And I told you at the beginning that you can get as many as 10 to the 75, 10 to the 80 particles in the state. Where's that number coming from? It's basically just the angular momentum of the black hole in fundamental units. So the black hole angular momentum from here to here decreases by 10 to the 78 h bar, and each of the particles in the cloud is carrying 1 h bar of angular momentum. So when it spins down, that's how many axions can make up the full cloud. So this is the same figure, but now showing the numerical evolution of the number of axions and the spin of the black hole as a function of time in years. So the black hole starts with a high spin with 0 particles. The number of particles grow exponentially and saturate at the point that the black hole drops down to this superradiance line, at which point the angular momentum extraction stops. But there's a parametrically longer process, which is the next level growing. In this case, it's level that looks like a d orbital. We started with a p orbital. The next level will start growing here. It's parametrically longer time because the wave function is localized parametrically farther away from the black hole. It has a larger angular momentum and a bigger angular momentum barrier. So the overlap of the axions with the black hole is smaller and superradiance is less efficient. So the next level will grow in a parametrically longer amount of time. Yes, please.
The question is, doesn't this process also change the black hole mass?
Good question. Yes, this process also changes the black hole mass. That's actually, I think, included in this picture, but you can't quite see it because it changes by a fractionally small amount. So the angular momentum is dominating here because you're putting the axions at a larger radius. So the same amount of mass carries a larger amount of angular momentum. So the angular momentum is the thing that gets exhausted first before the mass. But it is true that the cloud extracts mass from the black hole. And in fact, it can carry up to a few % of the mass of the black hole once the process is finished. So once these two levels form, the next level has again a parametrically longer growth time, and it will not really start to grow within the age of the black hole or even the age of the universe. So for all practical purposes, for this black hole, the first two levels will dominate the evolution. There's one behavior I want to highlight here, which is very interesting. After the first level grows, you can see that actually the population of axions decreases on a longer time scale. And that drop in the number of axions comes because this axion cloud is actually sourcing gravitational waves. So this cloud of axions has a large energy density. As I mentioned, it can carry up to a few % of the black hole mass. And it has a time dependence because the axions are rotating. So just as in your usual quadrupole moment calculation, it will emit some gravitational waves. It's actually a bit more complicated than that because the gravitational wavelength is quite small, but that's the general idea. So you have this time varying energy density shown here. There's a black hole, there's the cloud around it. And in the particle physics picture, you can just think of it as two axions annihilating into a graviton, but all of them are doing it coherently, and energy and momentum are conserved by the fact that the black hole has a potential, so that the axion momentum is not, there's a spread in axion momentum due to the gravitational potential of the black hole. And these gravitational waves that are emitted are coherent and monochromatic. And so that is both a great handle to look for them in laboratory experiments. So this is just to show you, again, this is a full numerical Girard calculation of the process. So this is a complete simulation of this cloud and its gravitational wave emission. Exactly. Axions, axions. Yes. So from the frame of the black hole, the gravitational wave emission looks very simple. The strain is just a sine wave with a frequency of twice the axion energy, which is about twice the axion mass. And it goes on for a very long time until the cloud is depleted through this process. Luckily for us, these kinds of signals, although they're not the ones that you heard in the LIGO discovery, which were violent mergers that were a few seconds long, these are searches that are being done at LIGO because they are very similar to what you would expect if you have a neutron star that's rotating, that's not quite azimuthally symmetric. So for example, if you want to see the gravitational radiation emitted from a pulsar, which has a small bump on it, this is the kind of waveform that you'd be looking for. And we proposed doing these kinds of searches with LIGO. And I'm very excited that today there's a lot of people who are on these gravitational wave experiments who are getting interested. So like 5 years ago, we projected that you can see up to thousands of signals in our galaxy that are emitted from rotating black holes. And more recently, I worked with people in the LIGO continuous waves group to look at the data and see if there are any signals. There's no signals, but we did confirm that you do expect to see if the axion exists and if there are quickly rotating black holes in our galaxy, these searches can pick up on tens to hundreds of signals. And that's something that will continue improving over time. And there's other strategies you can employ. Other groups have proposed looking for stochastic searches. So there's sometimes so many signals that you can look for excess power in a small band around twice the axion mass. And those are also searches that are being done with LIGO data. And more futuristically, you can look at products of mergers. So here I talked about, let's assume that there are many quickly rotating black holes born in the Milky Way. We do have evidence for that, but we don't know exactly how many there should be. But in a merger, we know that all the angular momentum, or most of the angular momentum of the merger, gets captured in the final spin of the black hole that's formed. So you know you're going to form a rapidly rotating black hole as a result of 2 neutron stars or 2 black holes merging. And if you have good enough sensitivity, you can follow up that new product and see if there's these continuous waves being emitted from it later. And that's something that we proposed right after the LIGO discoveries and is now being studied in more detail by, again, people on the LIGO collaboration. So I think this is a really exciting program to be doing in the age of gravitational wave astronomy. And one sec. And I think there are a lot more kind of observations and ideas to be had with current and future gravitational wave experiments. Question?
Why no photon rather than axion superradiance from black holes?
So the question is why axion superradiance but not photon superradiance? Good. So the key here is that the axion can form stable bound orbits around a black hole. Photon is massless, so it's not going to be able to form these kinds of bound states. There are some ideas on trying to look at, say, excitations of the plasma around the black hole, which would mimic the photon having a mass because of the electron number density. But these things are very lossy and very difficult to form. So as far as I know, there's no demonstrated superradiance with just photons. But that's, yeah, it's an interesting question.
So since there's no signal, can you put a constraint on this parameter space already?
Yeah, so we did not interpret the search exactly as a constraint for 2 reasons. One is that we were recasting data that was looking for these kinds of pulsars, and these searches were tailored to like one signal from a pulsar in a wide range of energies, whereas here you'd expect many, many signals clustered around twice the axion mass. So some of my collaborators were worried that the pipelines might not stand up to this large clustering. But since the paper, they've kind of gone in and looked at the data, and they can tell you that they're more convinced now that that's not the case. The other reason is that, and that's something that we want to do in the future, is we don't know exactly what the black hole populations are. So the number of signals will depend on how many quickly rotating black holes there are. And so any kind of exclusion will have to be kind of convolved with the assumptions in the black hole population. But very roughly, axions with mass around 10 to minus 12 eV are probably incompatible with reasonable assumptions about black hole populations. Any other questions about the gravitational wave searches before I go on to the next part? Yes.
So in the plot of the angular momentum loss you showed earlier, how sensitive is it to the axion mass that you assume here?
Good. Yeah, it's very sensitive. Well, not very. So it's a kinematic condition. It's not resonant. So it's not like you exactly have to match the black hole parameters to the axion parameters. But basically, the rate of spin down is proportional to the axion mass, and to, in this case, like 8 powers of this fine structure coupling constant that I told you about, which is the product of the black hole mass times the axion mass. So if you change the axion mass, the rate of spin down will change by if you change the axion mass by a factor of 2, the rate of spin down will change by 2 to the 8. But if you change the axion mass, if you decrease the axion mass by a factor of 2, and you increase the black hole size by a factor of 2, then the spin down will just change by a factor of 2.
So even without detecting any gravitational wave signal, wouldn't this already put some bound on the possible?
Yes, great question. So the question, keep forgetting to repeat the questions, I'm sorry. The question is if you can use the black hole spin down to put constraints on the axion mass, and the answer is yes, and I'll get to that in a few slides. Yes. Yes, please.
So is it known even how the signal would change if the super-radiant black hole is in a binary rather than being alone?
Yeah, the signal would definitely change. I mean, already you have to, of course, on Earth, the signal doesn't look like this because we're moving relative to the black hole. The Earth is rotating. So in the lab frame, you have to deconvolve all of these extra motions from this simple signal. In a binary, you can, again, add the motion of the binary onto that. But it just becomes more and more computationally expensive. There are tricks to try to look for these signals coming from binaries, also developed for pulsars. But now you have to kind of scan computationally over all the binary parameters as well as all of the black hole location parameters. And that just basically means you're effectively less sensitive for a given frequency than you would be for a single black hole.
The other question online is if it's known if super radiance has any effect on black hole binary formation or whether it is significant.
If super radiance has any effect on black hole binary formation. There are some interesting effects. If there's this cloud, I think to first order, there's not a big effect. It could be that the presence of the cloud, if there's a binary, it could affect the in-spiral. The incoming black hole can actually disrupt the cloud, and that can back react onto the in-spiraling object, which could push it out a little bit and change. Basically, the axion cloud will give up its angular momentum to the companion, and that can slow down the in-spiral. But I think these are fairly small effects, and they're being studied by some other groups to see if you can detect them in, say, LISA data. But to first order, I think the answer is no. OK, so in the last few minutes, I want to tell you about some recent work that I'm very excited about, which talks about how this story changes once we include axion self-interactions. So for those of you who are in the dark matter workshop, we talked today about the axion potential and the quartic self-interactions. And typically, they're very, very small. They're goes the mass squared over this high scale squared. but you have a huge number of particles in your cloud. So these self-interactions can actually be important. And so in this paper, we looked at what happens if you take the coupling of the axion from basically gravitational, which is the case for the QCD axion for these ranges of masses, to larger and larger interactions. And this is work with my collaborators, Marius, Robert, and Olivier, who were amazing collaborators. And I especially want to highlight Marius and Olivier, who are outstanding graduate students who are finishing up in the next year or two. So let's talk about what the story is here. So far we talked about superradiance, which is black hole grows a cloud of axions. You can have gravitational wave emission, where two axions annihilate and radiate gravitational waves. But in the presence of a quartic self-interaction, which generically you expect axions or axion-like particles to have, you can introduce two extra processes. One is what we call level pumping. So you can take two axions with angular momentum 1 and make one axion with angular momentum 2. And then one falls back into the black hole to conserve energy and angular momentum. So you can populate the next level from the first level without resorting to the black hole at all. Once you populate the second level, you can take two axions from the second level and put one back into the first level. And then you have enough extra energy left over that the axion can radiate off to infinity. So you have an extra energy loss mechanism. Just as a reminder of the gravitational story, what happens is the first level grows through superradiance. It depletes through gravitational waves. The next level grows through superradiance, depletes through gravitational waves. You never have two levels sitting around at the same time, basically. And all of the energy is coming from the black hole. If you have self-interactions, what happens is that the second level can be populated just through the presence of the first level alone through this quartic interaction. And now you have these new energy loss mechanisms where axions are falling back into the black hole and being emitted out to infinity. So there's while during the whole time, the black hole is still pumping out axions into level 1. So there's a quasi-equilibrium that can be reached, which is shown here in orange for comparison. So here's a gravitationally interacting axion. The orange is a more strongly self-coupled axion. For those of you who are familiar with axion parameters, here I'm taking FA of 10 to the 12, which is not excluded. It's kind of an interesting range of parameter space. So here, the first and second level grow simultaneously because as soon as the black hole starts populating the first level starts to pump the second level. And then they reach some quasi-equilibrium in which the superradiance is balanced by emission of axions to infinity. Since the number of axions in the level is much smaller, the black hole spin down is also reduced because the spin down is proportional to the number of axions in the cloud. So this is what I just said. The maximum number of axions is reduced because you have these new loss mechanisms due to axion emission, and the black hole spin down is parametrically slowed. Now that we understand how this process depends on this F parameter, we can go back to this, to your question from earlier of how we can use black hole spins to constrain axion parameter space. So we've already measured some black holes here, which have very high spins. I'm again showing the same picture as I showed at the beginning, which is the black hole spin on the x-axis, and the black hole mass, y-axis, black hole mass on the x-axis. But now this is actual data from X-ray binary observations. So these black holes, for this particular range of axion mass, fall well within the superradiance region. So we would have expected them to have spun down by today, given that we know they've been around for at least 1 million years or more. And this lets us set constraints in the axion parameter space with this new understanding of axion self-interactions. So as a function of axion mass, we take these 5 black holes that have been observed to have high spin and have well-measured masses, and we can use them to exclude a range of axion masses. As self-interactions increase, the spin down gets slower and slower. So at some point, we can no longer place a constraint once the axions are strongly self-interacting enough. And you can see that this is relevant for both the QCD axion parameter space and more general axion like dark matter space. So you might say, okay, well, this is great. I think it's very interesting that you can place these constraints. But it is a bit disappointing that up here, we're really suppressing the axion population around the black hole. So you don't no longer get gravitational waves because there's much less mass in the cloud. You don't get black hole spin down. So do we ever hope to see anything for these more strongly interacting axions? And their answer is yes. And in the last 2 minutes, I will tell you how you can look for them. So as I said, if you have these self-interactions, you can have this kind of 2-to-2 process where you take 2 bound axions, make 1 bound axion and 1 axion going off to infinity. This axion will have a velocity of about alpha over 6, where alpha is this gravitational coupling parameter. You can think of it as being between 10 to the minus 2 and 0.5, depending on how you, the ratio of your black hole mass and the axion mass. So this is generally faster than, say, axion dark matter locally in our galaxy. And you have this very long period. If you see on this x-axis, this goes up to 10 to the 9 years of axion emission, which is constant. So basically, the black hole is pumping this axions into the axion cloud, and the axion cloud is emitting these axion waves at constant amplitude throughout the age of maybe even the universe. And similarly to gravitational waves, you can look for these axion waves on Earth if if we're lucky enough that these axions couple to the standard model. So far, everything I've said has nothing to do with axion interactions with us. It's just the black hole and axions living in their own gravitational world. But if the axions do interact with the standard model, you can hope to detect these axion waves. And we think that with future experiments that are tailored to axion dark matter searches, you could see nearby black holes like Cygnus X1 or GRS 1915, which have high spin, emitting these axion waves and them being detected in the lab. So here I'm showing a sensitivity projections, the axion masses on the x-axis, and the effective strength of the axion coupling to nuclear spins, which is this particular experiment, is on the y-axis. And these lines are different projections depending on the sensitivity of the experiment and the coupling strength of the axion. So this is, if we're kind of more conservative, you have to be a bit lucky to see a signal. But in principle, all of this, these are still couplings which are completely open parameter space with slightly futuristic experimental assumptions. So in principle, we could see these axion waves emanating from nearby black holes, which I think would be very exciting. So to wrap up, I've talked today about how rotating black holes can produce these clouds of weakly coupled bosons through a process called superradiance. And this is a unique probe of weakly coupled axions or other light bosonic particles, including the QCD axion. These particles can spin down black holes, which already places exclusions in axion parameter space. And so there's gravitational waves, which are detectable with today's technology. And if axions have sizable self-interactions up here, they could be detected with future axion waves, could be detected with future dark matter experiments. To zoom out a bit, I think axions are a very special particle because they solve many outstanding problems and could even tell us something about high scales, which are never going to be reached with any kind of terrestrial experiment. And so I want to encourage all of you to think about what we can do to look for these particles. There's many great ideas already that I haven't put in this parameter space, and I'm happy to talk more about other experimental efforts that I and others are thinking about these days. But I think there's still room for lots of creative ideas in this parameter space. And today we talked about how stars and their compact object remnants can tell us something interesting in this very ultralight region of axions. So I'll leave you with this. I think something that I'm very excited about is that these black holes are a new source of axions in our galaxy. So we all know if we're in this field that axions can be produced in the early universe, or they can be thermally produced in the sun. And this is a completely new source of axions that we can look for that's coming from these rotating black holes. So thank you very much, and I'm happy to take more questions.
Are there any questions in the audience here? Please, yes.
How much of dark matter you would think such axions could be? How much of dark matter could be resolved by these axions? Or if you find them, would they constitute a very small fraction of dark matter? Because if they get created from black holes and stars, presumably there will be a small fraction of observed matter.
Yeah, the question is, how much of the dark matter could these axions make up that are produced, say, in this black hole? And yeah, I just want to be clear, the axions that are produced here would in no way explain dark matter, right? First of all, they're only produced after the black holes are formed and then emit the axions. But they are a small fraction of the energy density today. You can think of it as there's 5 times more dark matter as regular matter, and there's more gas than stars, and there's more stars than black holes, and then some fraction of the black holes go into the axions. So there are several suppression factors which make this a very subdominant population in terms of energy density. In terms of I do want to say though that for the experimental searches, there are things that help us, which is that they're moving much faster and they're more coherent. So you can do this experiment over a longer time and get better signal to noise. So you have to work harder to see these than dark matter, but it's not as bad as just that energy density ratio. Thank you.
It's like a very naive question, but you mentioned that these effects of superradiance will appear even if there's no initial action population, even if you produce like quantum fluctuations. Now, these quantum fluctuations intrigue me. So then, is some sort of a Hawking radiation procedure that appears here in the vector?
Yeah, I mean, so the question is how to think about these quantum fluctuations that could seed the growth of these states. And I mean, in principle, at any time, each of these bound states is populated by 1/2 h bar omega of axions. And the ones that satisfy the superradiance condition and have the fastest growth rates will be the ones that start to grow the fastest and dominate the evolution. It is interesting, the connection between superradiance and Hawking radiation. Some people like to talk about it as, the stimulated emission version of the spontaneous emission, which is Hawking radiation. And in fact, going back to Zeldovich, when he came up with the idea of superradiance and that black holes can actually do the same thing as regular rotating cylinders, that was kind of one of the first hints that black holes can act as thermodynamical objects. And Hawking then, I mean, it's not clear how much communication there was, but there are some interesting lectures, there's some interesting reminiscences by Kip Thorne that I can point you to about how he went back to the US and then talked to Hawking. Then Hawking came up with Hawking radiation, and then Kip Thorne went back to the Soviet Union and told Zeldovich, and he said, no, 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 there's no way this happens because the black hole doesn't have to be rotating and has to be rotating to emit the waves. And so he didn't believe it. And then after a while, he went back and did some calculations, or his students did some calculations, and he agreed. And for the rest of his life, he said that was one of his biggest failures, that he didn't come up with Hawking radiation. So
there's a question online. For black holes in the X-ray binaries, would you expect any effects of gas accretion on the Axion cloud?
great question. Any effects of the accretion on the Axion cloud? So there's two effects that you could think about. One is just the fact of accretion itself, that you're spinning up the black hole while it's spinning down due to superradiance. And that's something that for stellar mass black holes is not a big effect, because the fastest that you could accrete order 1 of the spin is about a salpeter time, which is like 10 to the 8 years. So all of these processes are much faster than that, but it's easy to take into account even if they're not. The other effect is just the fact that there's a large accretion disk which has mass, and in fact there's a companion that has mass, and that could cause a disruption to the Axion cloud, because remember, we're just solving it in this nice azimuthally symmetric potential. So now if you have a companion, that could mess up the existence of the cloud. And in fact, that's part of why these bounds end here. We're being a bit conservative, but we're saying if the companion frequency can match any transition energies between different Axion levels, it could cause transitions of axions from one level to the other and disrupt the cloud. And so here you'd have to do a bit more careful work to see if the black hole actually spins down all the way or not. So yeah, that's a great question.
Any questions here? If not, then let's thank Masha again for
Thank you. And I'm in, if people have more questions, as I said, I'm in Betty Hall. So here today and tomorrow. So feel free to come and chat more. Thank you.